Hey everyone, today we're going to be learning about elastic potential energy and how this relates to potential energy that we can store in a spring depending um, how we compress it or how we stretch the spring. And we'll be looking at a couple different demonstrations of this in class and how we can use this to our advantage and where we might use this in the real world. So we'll start with elastic potential energy. And elastic potential energy is energy that is stored in a spring, and it's stored when we do work that's either going to compress or stretch it. If you think about it, if you have a length of spring here, it's kind of a poorly drawn spring, but you get the idea. If we were to either compress or stretch that spring to try and make it bigger, that's maybe a little bit better. We stretch that out. We do work to actually have to stretch that spring to increase it and change its displacement from where it wants to rest. And if we stretch it like that and we let it go, the spring's going to want to collapse back on itself, and it's going to want to return to what we call an equilibrium position. But it's going to take work in order to compress or stretch that spring, which is going to build up potential energy. So by compression or elongation of the spring, we're referring to the change in spring length from what like I said, it's called from its equilibrium position. And that's the position where it's going to want to stay when it's at rest. It's neither compressed nor stretched. It's in its state of balance with no other forces applied to it. And we have to apply a force to that in order to get it to elongate or to compress. Otherwise, just sitting there, it's not going to want to do either or. And this amount of compression or elongation of the spring is directly proportional to the force. So the more force that we apply, the greater the compression or elongation of the spring, which should hopefully make a little sense. And from that relationship between the elongation or compression and the force, this is what we call Hooke's law. And that's going to relate the applied force with what we call the spring constant. We represent that with K, and it is multiplied by the compression or elongation. So K is going to represent what we call the spring constant. This is going to change for every spring depending on the type and the material. And it has units of newtons per meter. Newtons per meter. F of S is going to be our applied force that we apply to the spring to either stretch it or compress it. And since that is a force, it's going to have units of newtons. And X is going to be how much that spring was compressed or elongated. So X is the compression or elongation length. And I'm going to put in parentheses here displacement. And that's displacement from equilibrium. And since that is displacement, we will use units of meters. And that's Hooke's law. So looking at potential energy of a spring, if we apply a force and compress it, and we hold that there, that spring has potential energy stored in it, which you can then release and convert that potential into kinetic energy, which we will cover in our next topic. So according to Hooke's law, as we increase the force on a spring, X increases. We either compress it more or we elongate it more. So what's this mean? If we apply a greater force, X, our displacement from equilibrium, is going to increase. Or if we decrease that force, our displacement is going to be less. So if we take the average applied force on a spring, take the average, so we got our applied force F sub S bar, it's going to be equal to 1/2 kx. Where k of x would be the maximum force applied to the spring. So the work done in stretching the spring, if we want to find how much work is being done, it's equal to the product of the average force F sub S bar and the elongation, which I've been referring to as the displacement, which is X. So if you think of the spring, if this is equilibrium, we can compress it, let's call that a negative displacement, or we can elongate it, which would be a positive displacement. Either way, it's a shift from its equilibrium position. So work is equal to the average force times the elongation, which we broke down average applied force into 1/2 k times x. We multiply that by our other x here, which is equal to 1/2 k, and we'll combine like terms, into kx squared. That's how we can figure out how much work is being done to compress or elongate the string. Or spring, not string. Now work, we know, done on an object is equal to its change in potential energy. And the same idea is going to apply here. The work done on a spring is equal to the spring's elastic potential energy, PE sub S, which is equal to that quantity that we just derived there, 1/2 kx squared. Where k is the spring constant with units of newtons per meter. X is the elongation or compression length. And that's going to be measured in meters. And PE sub S is the potential energy that is stored. And since it's stored in the spring with units of, and since it's energy, it's going to be units of joules, or J. I'm going to do a couple examples here, and then I'll do a couple of these in class, but I'll get you guys started with a couple of these here. We have a spring that has a spring constant of 30 newtons per meter. So we have a spring constant We have a spring constant that has a value of 30 newtons per meter. Determine the magnitude of the minimum force required to stretch the spring 0.46 meters from its equilibrium position. So we want the minimum force required, which we don't know, in order to stretch the spring 0.46 meters from its equilibrium position. Well, we have 2 out of our 3 pieces of information to find the applied force on the spring. We take 30 Newton meters, multiply that by our elongation. Meters are going to cancel here. This will give us 13.8 newtons. We'll round that to 2 sig figs, which will be 14 newtons. So this took our spring, it was kind of like a light bulb, and we increased this distance 0.46 meters. So we stretched that spring out, and that took a force of about 14 newtons. Number 2. A 55 Newton weight is attached to a spring that is 0.62 meters unstretched. The weight caused the spring to be a total length of 1.36 meters. What is the spring constant of the spring? So, we have a spring here, unstretched, it's 0.62 meters. I should probably draw this vertically, considering something is hanging from it. So this is 0.62. And I'm not going to want to call that x. Let's call that a distance of 0.62 meters. We have a weight that's hung onto the spring, which causes this spring to elongate based off of having a weight attached to the end of it. And now the distance is 1.36 meters. What is the spring constant of the spring? Well, let's see what we know. We know that we have a 55 Newton weight attached to here. See if I can draw that. And that's going to be 55 Newton weight. That's going to cause that string to elongate. So we can figure out what our elongation is here by looking at the final measurement of 1.36 meters and subtracting the equilibrium position. This will give us the displacement of the spring of 0.74 meters. This is the difference from its equilibrium position to where it was stretched. And that's 0.74 meters. We know the applied force on the spring is 55 newtons, and that's from the weight that's attached to the end there. And from that we can figure out our spring constant. So we know that the applied force equals spring constant times elongation. So K is going to equal our applied force over our displacement, which is 55 newtons over 0.74 meters, which gives us a constant of 74 newtons per meter. I'm going to save the last two for you guys for class. On our next video, we hope to have a cameo appearance by one of your favorite teachers here at Sally High. For now, I'd like to share a story with everyone. The other day, I was in a conversation with Levi, and we were talking about the drone program here at school. And he told me that recently, him and Mr. Strauss, who's our STEAM coach, they were talking, and they were trying to set up a drone surveying program. They're hoping to get together and be able to do some surveying for different farmers in the area. And they were trying to come up with a name for their company. And they came up with a really good one, which I thought was great. They were planning to call it Levi Strauss. Have a great day, guys.